Now everyone, let's gear up for the geometry problems. So what are my geometry problems now? Geometry problems are actually involving when I'm joining various points, trying to form straight line, trying to form triangles. So it's a very simple thing. For straight lines, you need 2 points. For triangles, you need 3 points. And then accordingly, we'll decide what exactly we want here. Right, let's quickly start with it. It's a pretty simple concept, very quickly absorbed. I want every one of you to be very, very focused over the screen and note down the things while learning very quickly, as it is comparatively much easier to understand, right? Because in geometry, you can see a lot of things happening here. Let's begin with, if there are n points in a plane, none of them are collinear, right? No three of them are collinear. Sorry, not none. No three of them are, because any 2 point will only form a line. So no three of them are collinear. Then by joining them, we can obtain. Assume that, let's say if I have these 4 points, P1, P2, P3, P4. Okay, so for these 4 points, if I want to join any two, I'll be generating lines. So let's say if I join P1, P4, I'll be joining one line, or I'll be getting one line. If I join P2, P3, I'll be joining, or I'll be getting one line. If I join P2, P4, I'll be getting one line. Right, so what is that? You just need two points, right? You just need 2 points on this, right? It's exactly quite similar to the logic when we have that number of handshakes. For handshake, what do you need? You just need 2 folks, right? For the number of handshakes. What do you need here? You just need 2 points. How many points do you have? N. How many points do you need? Right? So it's just that equal to number of handshakes. So basically you just need 2 folks from the n folks. And from that, I can say that I'll be having how many straight lines? NC2 straight lines. Out of n points, I'll be choosing any 2. That will give me the number of straight lines. Perfect, sorted. Okay, now let's quickly move on to the next one. If I want to have the triangles, I need to have 3. So let's say if I've joined that P1, P3, P4. Can you see the other one? P1, P3, P4, P1, P2, P4, right? So various triangles are possible, right? So for triangle, I need to have 3 points. So how many number of triangles I will be having? I will be having the number of triangles as is equal to NC3. So out of n points, I just need to choose any 3 points. That will give me what? NC3 number of triangles. Perfect. Okay, so for number of straight lines, we need NC2. You just need to choose any 2 points because none of them are collinear. No 3 of them are collinear, I'm sorry. And then for triangles, I know that no 3 of them are collinear, right? So NC3, you choose any 3 points, they will form a triangle. Sorted. Now, let's take up the case when the things are not that smoothened, right? There are some points which are collinear as well. So there are n points in a plane of which m points are collinear. Then we have to predict the number of triangles and number of straight lines. Perfect. See, these 3 points are collinear. Can you see these 3 color change ones, the yellow ones, right? And the other 2, they are just random points. So only these 3 points are collinear and the other 2 are not. Okay. Now, if I have to predict the number of straight lines, can I call the number of straight lines as NC2? No, I can't. Why? Because if I join these 2, I get a straight line. If I join these 2, I'll get a straight line. But what happens if I join this? If I join these 2 points, if I joined all these points, what do I get? I'm repeating that line again and again and again, right? So as many number of collinear points will be, they will be effectively forming only one line, right? And if I try to do directly counting by NC2, I'll be actually adding up so many numbers. So then how should I remove that? So let's say if there have been no restriction, all of them would have been like no 3 of them would have been collinear, NC2 number of straight line would have been there for sure, right? But I know that out of those m are collinear, so I need to subtract those MC2 number of lines which will be forming by joining these 2 or these 2, which I've pointed again and again. But by removing MC2, I have removed all such lines which are actually formed by joining these points. And I know that if the points are all collinear, they will surely form at least one line. So what do I need to do? I need to add that one here. Do you understand? NC2 is the total number of possible lines minus MC2, all the possible lines which I am getting from those collinear points only. But I need to count that line once because even if they are collinear, they will definitely form at least one line. So I need to add that one here. Understood it? Sure? Let's talk about the number of triangles. Can I report my answer as NC3? No, I can't. Because if I choose these 3 points, can I form a triangle here? No, I can't form a triangle with these 3 points. They will be collinear. How many points do I have in collinear? M. How many such triangles by mistaken we have counted? MC3. The way you will be choosing any 3 points from those m collinear points. So choosing any 3 collinear points from those m collinear points will give you faulty number of triangles, right? So from total number NC3, you need to remove the cases where all the triangles which are formed with the help of collinear points is definitely going to subtract it. Now here I don't need to add or something, because even if the 3 points are collinear or something, or any number of points are collinear, they cannot form any triangle, right? So the answer becomes NC3 minus MC3. Pretty simple and sorted one. Okay, so what do I have it here? Let's quickly move on to the one application of it. If I want to deal with the number of diagonals of a polygon of n side polygon, so we can have a triangle, right? Do we have any diagonal here? No, we don't have. Okay, let's say if I go to any square, do we have a diagonal here? Yes, we have this, so we have 2 diagonals here. Let's talk about pentagon. How many diagonals do I have? 1, 2, 3. So we have 3 diagonals here. So the problem is, like, in fact, we have some more. So we have this also and we have this also. So basically we have these 5 diagonals here. Then how shall I predict it? So that was the case of pentagon or square or hexagon, we can draw it. Somebody asked it, let's say if I have a 20-sided polygon and if I want to have the number of diagonals, of course you cannot count it. Then how will I be doing it? Understand it. See, by NC2, what I'm doing, I'm just trying to find out all the possible lines. Okay. So diagonals are lines, of course. But this NC2, when I'm taking up any 2 vertices, this NC2 will give me these lines also. Let's say if I consider that square, so it will give me this line, which is a side. Or on a pentagon, it can give me this line, which is also a side. Do you understand what I'm trying to say? How many such combinations of NC2 will be there, or in NC2 will be there, which will actually form the sides? That will be equivalent to nothing but the number of sides of that polygon. So NC2 is the number of combination of selecting 2 points, right, out of those given points. So let's say in square we have these 4 points. If we choose this point and this point, we get a diagonal, no worries. We choose this point and this point, we get a diagonal, no worries. But the moment when I choose any 2 adjacent point, I will be getting a line. I will be getting an edge. So what I have to do, NC2 gives me all the possible number of straight lines formed with the help of that geometry. That will include the sides as well as diagonals. But what do I need to remove here? The number of sides. So what is NC2? Number of possible line. N is the number of sides. So from that all possible number of lines joined by any 2 vertices of the polygon minus the number of sides of that polygon, what that gives me? That gives me nothing but the number of diagonals of that polygon. Numerically, it turned out to be nothing but n into n minus 3 by 2. Very simple calculation. You can do it any moment of time. Just figure it out. NC2 is n into n minus 1 upon 2 minus n will give you n into n minus 3 by 2. So total number of possible sides which can be, total number of straight line that can be formed with the help of the vertices of a polygon. So if a n-sided polygon, it will have n vertices. I can choose any 2 vertices by NC2. That will give me all the possible diagonals as well as sides. From those number NC2, I need to subtract the number of sides, that I'll be left only with the number of diagonals, which will numerically become equal to n into n minus 3 by 2. Sorted? Lovely. Let's quickly move on to one very interesting application of it. And everyone, please be very careful while listening to this. Please note it down. If a set of m parallel lines are intersected by another set of n parallel lines, so I have m parallel lines and another set of n parallel lines, then I want to have number of parallelograms. So I've given with m parallel, so please see the diagram. So m set of parallel lines and here another set of parallel lines. So every set of parallel line, right, 2 parallel line here, the blue colored one, 2 yellow one, they will actually form this parallelogram. Can you see that highlighted one? Right, let me show you. This highlighted one, can you see that? Okay, lovely. So this is how the parallelograms will be forming. Now let's say if I increase one more yellow line, I'll have one more parallelogram here, right? The bigger one and even the smaller one also. So if I keep on increasing the number of sides, then of course the number of parallelogram, the dimension will also be increasing, as well as the number of parallelograms will also be increasing. So let's say this is what the general scenario. I have m parallel sides, I have another set of parallel sides, n parallel sides. Now I have to count a parallelogram. So how do we form a parallelogram? For any parallelogram, I need 2 parallel sides here, I need 2 parallel sides here. So from this set, I need 2 and 2 sides, and from this set, I need any 2 sides. So let's say from the first set, m, I choose any 2, followed by From the another set n, I choose any two. How many sides do I have? 4. 2 here and 2 another set. 2 first set and 2 from the given set. What do I have? We have this kind of parallelogram possible here. Every combination of two parallel sides from one set and two parallel sides from the other set will form one parallelogram. So how many number of parallelogram? MC2 into NC2 will give me the total number of parallelogram. The number of ways in which you can take up two parallel sides from one set and you can take up two parallel sides from the other sets. Sorted? Everyone, please note it down. MC2 into NC2, the moment you have two parallel lines from one set, you have two parallel lines from the other set. From these two parallel sets, you'll have one parallelogram. So total number of parallelograms are equal to the number of ways in which I can choose two parallel sides from one set and two parallel sides from other set. That is MC2 in succession for the other parallel sides, NC2. So MC2 into NC2 will give me the answer. Sorted? Okay. Wow. So there were so many things that we have covered. Let's quickly see what does we are actually now left with. Very simple observation. One more that we'll do quickly. The maximum number of points of intersection of what? I want to see the possible number of intersection, the maximum number of point of intersection. So let's say there are n straight lines in a plane, right? And none of them are coincident lines, right? So no lines are coincident, none coincident. All of them are different lines. Perfect. So if I want to have maximum number of point of intersection, so can you see if I take up one line, if I take up another line, for every two line will give me one intersection point. That's it. So how many intersection point? The way you choose any two lines, you will be generating one intersection point. How many ways you can choose two lines? NC2 into 1, because every combination of two lines from NC2 will give me one intersection point. So how many intersection point? NC2. Right, perfect. Okay, so as I said quickly, you take one line, you take another line. This is what the intersection point that I'm talking about. If you take up another line, then we'll again have this intersection point as well as this intersection point, right? So what do I have it here? The total number of intersection point, if I want to mention here, there will be nothing but is equal to simply NC2, right? So I can say that the total number of straight lines will become equal to NC2. Perfect. Okay, now let me move on to now the circles. So let's say if I have n unequal circles, right? Because if I have equal circle, they might coincide, right? So I don't want to take into that thing. I have n unequal circle. You take up any two circles. If they are intersecting, they will intersect at 2 points. Somebody might say, sir, the circles might touch each other. Yes, of course, right? Then only one intersection point. But what I'm interested in, the maximum. If I'm interested in maximum, I'll make sure that they intersect at two distinct points, right? I don't want to take up the case of tangency, right? Okay. All right. So that's what my idea is. If you take up any two circles, they will surely be intersecting at 2 points, right? So these are the 2 points that we have. So the number of ways I can choose any two circles multiplied by 2 will give me the number of intersection point of that. So basically that's how my picture look like. So these are the number of intersection point that the two circles can have. And numerically it is equivalent to NC2 into 2. NC2 is the number of ways I'm choosing any two circle, and every intersection of two circles in the maximum possible fashion can give me two intersection point. So NC2 gives me the number of ways I'm selecting a pair of circles, and every pair of circle after intersection can give me two maximum intersection points. So NC2 into 2. Got it? So let's quickly apply the concept into this particular question. So there are 12 points in a place of which 7 are collinear. By joining them, we can have first option, number of straight lines. Second option, number of triangles. Not second option, in fact, the second case. Then the third question, or the third part of the question, is number of circles. And the fourth part of the question is number of pentagons. All right, so let's quickly start doing it by understanding the basic geometrical thing. So if I want to have the number of straight lines, a straight line can uniquely be defined by joining any 2 points, right? So out of 12 points, I will be choosing any 2. That will become 12C2. Perfect. But there will be a mistake in that. We have 7 collinear points, right? So out of these 7 points, if I'll be choosing any 2 of them, they will every time form the same line only, right? Let's say I have these, like how many points? Let's say 6 or 7 points are there. If I join these 2 points or these 2 points or these 2 points or any 2 points, they will every time give me the same line, right? So what will happen? In this 12C2, when I'll be choosing any 2 points out of these 7 collinear points, we will be actually counting the same line again and again, right? So what I have to do, I need to do that subtraction. That is, from 12C2, I will be subtracting 7C2. That will be the number of lines which I have counted extra, right? But ultimately that is one line, right? So I need to add it once. Perfect. So we get this as 12C2 minus 7C2 plus 1. Simplify it, we'll get your answers. All right, sure? Everyone gets it? Perfect. Okay, so after the number of straight lines, we needed any 2 points, right? And then we calculated it. The second part of the question says that I want to look for number of triangles. For number of triangles, I need to have 3 non-collinear points. Perfect. So let's quickly take the count from that logic itself. If I have 12 points and I need 3 points to form a triangle, so the total number of possible triangles would have been 12C3 had been the case when there are no collinear points. But here we have 7 collinear points. Every time I'll be choosing any 3 points from those 7 collinear points, we will be actually leading to no such triangle, right? So I will be actually including those extra triangles in this particular 12C3 number, right? So in these total number of triangles, I will be subtracting the ones which are formed by, or rather which we have mistakenly counted by taking any 3 points out of those 7 collinear points. So choosing any 3 collinear points out of 7 points is what? 7C3, and that's why we have subtracted 12C3. We have subtracted 7C3 from 12C3. All right, sorted? Perfect. Now, third part of the question is actually a very simple one. They're asking me the number of circles. See, in order to have a circle, you need to have 3 non-collinear points, right? Or in other words, if you say the number of triangles and every such triangle will actually generate a circumcircle to it, right? So the moment if I have a triangle, then I can have a circumcircle of it. So as many number of triangles, that is equal to as many number of circles. Perfect. You guessed it right. So the answer to the third option or the third part of the question is exactly equal to the number of triangles, because every triangle will have a circumcircle, right? The number of triangles which we have counted here, for every triangle will have a circumcircle. Perfect. Sorted. A pretty simple one to handle. All right. Now the interesting part comes when I have this number of pentagons. All right. So for the number of pentagons, we need to choose any 5 point. Let's say if I take up the value as 12C5, but I will be making mistake. Why? Because I have 7 collinear points. So there can be a possibility when I can choose all the 5 points from those collinear points. So I need to remove that, right? See, 12C5 will be the total number of cases when I'm choosing any 5 points out of those 12 points. But I need to remove the cases when I have chosen either 5 points from on those collinear, which are collinear, or I have chosen any 4 points which are collinear, or I have chosen any 3-point collinear, right? Because in that case, I cannot have. Assume that if I have 3 collinear points, right, they will form a line only. And even if I have 2 other points, they will actually form a quadrilateral. Are you getting my point, right? So it becomes a bit difficult for us to calculate in that way. Perfect. Okay, so how should we do that? From the total number of cases, I'm subtracting the number which is 7C5. By mistakenly, I have counted these as the number of pentagons, but if I'm choosing any 5 collinear points and if I'm joining them, I'll get a straight line, not the pentagon. So that I've removed. Perfect. Then by mistakenly, I can choose any 4 points from those collinear points, right? And any 1 point from the rest of the 5 points. So that is 7C4 into 5C1. Now what is there? If I have 4 collinear points, they will form a line. So I have 4 collinear points, I join them by a line, and then we have to choose any other point from the rest of the 5 points. They will actually form what? They will form a triangle. Are you getting the point? Right? Pretty simple to handle. Okay, so they are again not going to give me the pentagons. Perfect. That was the case. Now another thing which we need to subtract is if I am choosing any 3 points from those collinear points, right? Let's say if I have chosen any 3 points and I have taken up 2 more random points anywhere else. So these 3 points will actually form a line, and when I join them by the other 2 points, we'll get a quadrilateral, not a pentagon, right? So I need to remove the cases where I'm choosing any 3 points from those 7 collinear points, followed by I need to choose any 2 other random points from the rest of the 5 points, that is 5C2. Perfect. So from the total number of cases, I've subtracted 7C5, then I've subtracted 7C4 into 5C1, then I've subtracted 7C3 into 5C2. All right, because these will be the extra number of counting which we have done in 12C5. So from the total cases, I have to remove these cases where no such pentagon would have been formed. All right, understood? Perfect.